So I've started recording. Let's see, do we have a chat box somewhere? God, what did I do? Did I just blow the meeting away? Can you guys still see me, or did I click on the wrong thing?
It looks like you stopped screen sharing, but we can see you otherwise.
Yeah, well, seeing me is no point in seeing me. How the hell do I restart screen sharing? I don't see the bar anywhere. Oh, here we go, share screen. Yeah, sorry, I clicked on the wrong thing. All right, so presumably you can see the screen now. Hello?
Yes, we can.
Okay, good. All right. Okay, so I guess I'll start. I think I might start with something completely different that is sort of an application of the Fourier analysis that we learned a few weeks ago. You know that the phase factor of a single particle in quantum mechanics is basically e to the I px minus omega t. Here I guess I've set h bar equal to 1 and gone to some sort of natural units. Anyway, the never mind about the units, and let's just focus on the p dot x part. You might have wondered how it is that in a composite system, you can think of a composite system as one big object with a phase e to the I p x bar, where p is the total momentum of the object and x bar is the average position. For example, if you're talking about a tennis ball in a tennis match, p is the momentum of the tennis ball, x bar is the center location of the center of the tennis ball. And you might say, well, you can also think of the tennis ball is composed of molecules, each of momentum pi at position xi, and then the phase factor would be a sum of pi xi. And you might wonder, how does this work out? And in the colloquium on Friday showed us on one slide, early in the colloquium actually, the work of I don't know, German or Austrian physicist named Arndt. And he was exhibiting the interference of macromolecules, organic macromolecules, with an atomic weight of around 2,000 or more. So I worked something out and put it as example 4.3 in the notes on the class notes that are called examples. And so let me just take you through it just briefly. The sum of pi xi is, you can rewrite it as the total momentum times the average position plus a sum of over the individual molecules or atoms, or equivalently the individual quarks and leptons and gluons, with momentum pi, and p bar is the average momentum, xi is the position of the ith particle, and x bar is the average position of all the particles, defined like this. And using the repeated indexes to mean summation, one can verify this identity. Let's skip the Lagrangian thing. The point then is that the phase factor, if you view the tennis ball as a bunch of molecules, then the total phase factor would be the product of the phase factors for the individual molecule, because you can write it as the momentum of the tennis ball, the center of the tennis ball, and then these things, which are the difference, the momentum differences times the position differences. But of course, the positions aren't that different from the average position, and the momentum, each momentum is close to the average momentum, because after all, the tennis ball is not splitting up into individual particles. So if the n particles are bound together as one object, then we have these epsilon and delta to describe the xi and pi. And this identity up here shows you that the sum of all the individual phases is the total momentum times the average position plus a bunch of quadratically small terms. In other words, here, if we let xi be x bar plus epsilon sine omega I t, I'm thinking of these individual atoms as, or electrons or whatever, as being in some sort of a harmonic well about their minima, and the same thing for the momenta, then the phase is quadratic in the small quantities. And so I wrote a MATLAB script, which is reproduced here. You can probably write a much better script. But anyway, the point is that it's a small, the deviation from the average phase is quadratic in the, or second power. It's proportional to epsilon times delta, in other words, times sums. And it turns out to be sine of 2 omega I t over 2 summed. And so what one gets is that the blue curve is the exact solution, and namely this exact phase here, or equivalently the left-hand side, and the red dashed thing is the average phase. And you can see that they track pretty well. And this is for the case where epsilon and delta are 1/3, and there are 100 random frequencies. I took the omega I as just random numbers. So this is why an object made of many particles bound together appears quantum mechanically, and for that matter, classically, as a single object. The effective wavelength, though, is very small, namely h bar over the total momentum. So experiments that show their interference are difficult. Aren't, I gave you a reference here, exhibited the interference of complex macromolecules, and the formulas are here. The big term comes from PC, which is phthalocyanine, and you can see the diffraction there. So he has to basically have the velocity of these macromolecules be very, very slow in order to get this interference pattern. Anyway, I thought it was actually the best part of the colloquium, but others may have other views. Anyway, meanwhile, back in Legendre country, first of all, before going on, where is our chat thing? I thought, oh, Jesus, I stopped, shit. I stopped share screen again, damn it. Sorry about that. Let me just see, where is the chat thing? There it is. Does anybody have a question? Because I think it's really important in these Zoomed lectures to have student feedback. And I think it's all right to talk also. So if you want to shout out a question or type it in the chat box. All right, well, I haven't heard any yet. So let me just review some of what we said about Legendre polynomials, I guess last Thursday. The ordinary powers of x to the n, are form a complete set of functions, but they're not orthogonal. And so what Legendre did was to insist that the polynomials be orthogonal and be normalized. And the cute way of making them orthogonal is to say that the polynomial of order n, in other words, the highest power of x is x to the n, should integrate to 0 when multiplied by x to the m if m is less than n. And that gives you the Legendre polynomials. Here are the first 20. They're bounded by 1 in absolute value. Rodriguez developed a very nice formula for them, namely the nth derivative of x squared minus 1. And you can then get a nice formula for them in terms of squared binomial coefficients. And so I'm going through this because quickly because we've already done it. The integral of 2pn, pn with pm vanishes unless n is equal to m, and the total value is 2 over 2n plus 1. This is a very nice generating function that shows up all over physics. Another way of saying it is 1 over square root of 1 minus 2xt plus t squared is an infinite sum of t to the n times the nth Legendre polynomial at x. And this is used to express the distance between a point capital R and a point lowercase r as this sum. This is for the case where little r is smaller than big R. And so it's this sum here. And that follows from the generating function. We got to Legendre's differential equation, and in self-adjoint form, it looks like this, primes meaning d by dx. And consequently, the eigenfunctions are orthogonal and complete. And they're complete because the eigenvalues, you see the eigenvalues here are n plus 1. They go to infinity as n goes to infinity. And so these guys are complete. And I showed you a particular delta function. Well, it's the delta function the Legendre polynomials generate. And in physics classes, we often change variables. And so we set x equal to cosine theta, and then sine squared theta is 1 minus x squared. And then we say d by d theta, well, is d by dx, dx is cosine theta, so d cosine theta d theta, and that's minus sine theta d by dx. Or equivalently, d by dx is minus 1 over sine theta d by d theta. And in those terms, the Legendre, in fact, the self-adjoint form of the Legendre differential equation is this. Let's see, I think I can make this somewhat bigger. I can also maybe move this thing out of the way, and I can make it bigger. Let's go up to that maybe. So I mentioned there are various recurrence relations. I've never been all that interested in them. There are special values of the Legendre polynomials. Pn of minus 1 is minus 1 to the n. Pn of 1 is 1. That was Legendre's defining condition. Pn of minus x is minus 1 to the n Pn of x. And that means that the odd ones must vanish at the origin. This is an interesting relationship between the Legendre polynomial and the Bessel function. Schläfli had used Cauchy's integral formula and Rodriguez's formula to write the nth Legendre polynomial as this integral. And Rodriguez's formula can also be used to generate other families of orthogonal polynomials. In fact, you could amuse yourself by defining a new family of orthogonal polynomials, I guess, by choosing the W's and the function W and the function Q as you please. W turns out to be a weight function. That's why it's called W. And typically you want Q to vanish at the two ends of the interval that we're talking about. So it vanishes at A and B. So then, as long as Q vanishes at the endpoints and the R's, the Rodriguez polynomials, that's are defined this way, then they're orthogonal with the weight function W. And there's then some normalization n sub n. I didn't, there's probably a relation between n and en, but I don't have it handy, and I don't know how simple it is. There are various examples. You can set Q equal to x squared minus 1, which of course is the choice in the Legendre polynomials. And you can then choose this weight function where alpha and beta are typically real and greater than minus 1. And the normalization then is En is 2 to the n over n factorial. And these are then orthogonal on minus 1 to 1. And the orthogonality is that it's proportional to delta nm, and you have this huge factor, this complicated factor in front. Their differential equation looks like this. And here's a Rodriguez type generating function. You notice it's the same form essentially as for the Legendre polynomials. If you set alpha equal to beta, then the Jacobi polynomials become the Gegenbauer polynomials. And if you set alpha equal to beta and equal to beta equal to plus or minus a half, they're the Chebyshev polynomials. You set them equal to 0, they're the Legendre polynomials, and these are some recursion relations. The choice Q equal to 1 with a weight function e to the minus x squared leads to the Hermite polynomials, which these are not quite the same thing as the Rodriguez polynomials, because there the interval's finite and you have Q vanishing on it. Here in the Hermite case, your interval goes from minus infinity to plus infinity, and you've got W vanishing at the endpoints. Anyway, the generating function is quite different. And so these are the wave functions of the harmonic oscillator. Then to get back to the Rodriguez type, if you said, well, actually, this isn't quite Rodriguez either. You said Q of x equal to x, and this particular weight function, you then get generalized Laguerre polynomials. And notice here, you're only considering an interval from 0 to infinity. And so so you've got the weight function vanishing at both ends, at least if alpha is positive. And And these then are orthogonal on the interval 0 to infinity and satisfy this differential equation. And their generating function is rather complicated here. And these are the wave functions for the various states of the hydrogen atom in the non-relativistic hydrogen atom. Okay, so let's turn now to the application of Legendre polynomials to differential equations. In a spherically symmetric problem, you have the Laplacian occurring often, and it separates, of course, in spherical coordinates, as we saw back in section 7.3. And if there's no dependence on one angle, phi, then we have azimuthal symmetry, and things are simpler. And so we don't have to talk about phi, and we can just talk about theta sub L of theta. And that will be a solution of Helmholtz's equation if R and theta satisfy these two equations for a non-negative integer L. And then we can, this equation is the equation, differential equation for a Legendre polynomial. And for positive K, the solutions of the radial equation, these ones here, that are finite at R equals 0 are the spherical Bessel functions. And the spherical Bessel functions are rather simple, nice functions. They're just simple derivatives of sine x over x. And so these are nice. And if you think these are nice, and when I say they're nice, what I'm thinking of is the cylindrical Bessel functions are much worse. And the reason is that a cylindrical Bessel function is dealing with the Laplacian and cylindrical coordinates, in which you've assumed basically cylindrical symmetry, which is much less than spherical symmetry. So spherical symmetry gives you a higher degree of symmetry. And so you have simpler functions. By the way, I'm a little concerned that I don't see the green border. Do we still have, you guys still see the screen?
Yep, we're good.
Okay, all right, thanks. So let's see, where was I? Yes, the spherical Bessel functions are quite nice, and rarely, it turns out, derived this formula. And so the general azimuthally symmetric solution of the Helmholtz equation, that's this equation, that's finite at R equals 0 is a sum of this form. The AKL then are constants, and you can, it's a linear equation, so you can add all sorts of, well, that's what we've done here in this sum. We've added up all these different solutions. If the solution can be infinite at the origin, and there what one is dealing with is, for example, you're trying to do the physics outside of a certain sphere. Well, if you're talking about the region outside of a sphere, you don't worry about the behavior near R equal to 0, near the radius equal to 0. And then you can use the spherical Bessel functions of the second kind, which are also called Neumann functions. In the book, I used N for Neumann, but when I looked in section 10.5, I saw that I actually used a little y in 5, so I decided to go with y, which seems to be the more common notation in the literature. I'm not actually certain what's the best notation, but anyway, you've got to use functions that are also fairly simple, but you see, they're, instead of being sine x over x, which is regular at the origin, they're cosine x over x. And so there's a singularity built into the origin. And so the general solution then is a sum of the two different kinds of spherical Bessel functions. And when k is 0, then Helmholtz's equation just reduces to Laplace's equation, which is Coulomb gauge electrostatics or Newtonian gravity, and in the absence of mass. And then the radial equation is simpler, and we just set r sub l equal to r to the n, and substitute in this equation, we see that nn plus 1 has to be ll plus 1. And there are two solutions there. Obviously, n equals l is a solution, but also n equal minus l plus 1 is a solution. So the general solution looks like this. And so you see what's happened here is that instead of the spherical Bessel functions, we've got much simpler things, r to the l and 1 over r to the l plus 1. And if the solution has to be finite at the origin, then all the BLs have to vanish. So this was the case of no phi dependence in and spherical symmetry. So we have these simple solutions. We can also think of this as a solution in 2 dimensions. And if we just start with the cylindrical, the solution of Helmholtz's equation in cylindrical coordinates, then we have some capital rho of rho, capital phi of phi, and capital Z of Z. Then the equation for the radial function is Bessel's equation, which of course, we've seen many times. If k equals 0, then we just have Laplace's equation. And if f is independent of z, then the solution's even simpler, because now we have both alpha and k equal to 0. And so if we say that phi double prime sub m is minus m squared phi sub m, then the equation 730, which is the separated equation for the radial function, just becomes this. And in this case, phi, in order to satisfy this equation, we can take it to be e to the im phi, or a linear combination of cosine and sine. And now you then have to ask yourself, are we trying to solve a problem that has the whole circle of phi from 0 to 2 pi as physically relevant? Or are we just trying to do the physics in some region that's a wedge? And if the whole range of phi is physically relevant, then phi must be periodic and m must be an integer. Actually, I've actually got this a little wrong, right? Because I left out a 2 pi. So there's, right. No, I'm sorry, it is correct, because when phi, the 2 pi is built into phi. Okay, sorry. So in that case, the solutions are just e to the im phi, or, as you know, linear combinations of e to the im phi give you cosine and sine of m phi. And then the equation for the radial function, it's just rho to the n, and then we see that that n squared has to be m squared, so n is equal to plus or minus m. So the general z-independent solution of Laplace's equation in cylindrical coordinates looks like this. Okay, so now what about the general case, which is Helmholtz's equation in spherical coordinates. Well, we know that the Laplacian separates in spherical coordinates, and so we write f as a function of r times a function of theta times a function of phi, and that'll be a solution if r is a linear combination of spherical Bessel functions. Oh, I see, I didn't leave it. I've still got an n there. Let me write an index and note to myself, that's equation 9.94. Anyway, so we set R to be a linear combination of the two kinds of spherical Bessel functions. We let phi equal e to the im phi, or phi or phi, and capital theta, Lm, satisfies the associated Legendre equation. So this is what we saw back in section 7.3. And it turns out this associated Legendre function is just a multiple of what is called the associated Legendre polynomial. And they differ by a big square root and a phase factor. Okay, so in many of the spherically symmetric problems in quantum mechanics in 3 dimensions, especially in non-relativistic quantum mechanics, what you're dealing with is basically this function, and so you just so the tricky part is this radial function, and these are just the standard spherical harmonics, apart from an overall factor. If the whole sphere, all 4 pi steradians, are physically relevant. And whether you need the n's or y's, that is to say, the spherical Bessel functions of the second kind, the ones that are singular at the origin, whether you need to include these depends upon whether the region near the origin is physically relevant. If it is physically relevant, then typically you toss these aside. Okay, so let me go on to the associated Legendre polynomials. These are polynomials in x, which is cosine theta, and in sine theta, which is square root of 1 minus x squared. And they arise as solutions of the separated theta equation. So they're this equation. So it's basically the theta equation of the Laplacian in spherical coordinates. So you have an equation that involves a Laplacian, for example, the Helmholtz equation, or the equation for a particle in a spherically symmetric potential. You then have an angular equation that looks like this. And if we go from cosine theta to x, then we have this self-adjoint ordinary differential equation. And this associated Legendre polynomial is simply related to the nth derivative of the Legendre polynomial. So PLM, which is the associated Legendre polynomial, is related to the, here parenthesis m parenthesis means the nth derivative. I probably should have written that explicitly. So let me write that down. Of the ordinary Legendre polynomial. So in other words, the associated Legendre polynomial is this factor times the nth derivative of the Legendre polynomial. And so what we do to check that this satisfies this equation is we take this definition and invert it. So we write the nth derivative as PLM times this factor. In other words, we just sort of invert this equation. We differentiate it twice and we get this. First derivative is this, second derivative is that. Then we use Leibniz's rule. Remember that Leibniz's rule is that. We use Leibniz's rule to differentiate Legendre's equation. which was, well, just the equation for a Legendre polynomial. We differentiated m times. So we go from, in fact, there's Legendre's equation. I don't know why I had to go back there. We differentiate this equation m times, and then we get this expression. Now we take these equations and stick them in here, and we see that they obey the desired differential equation like that. In other words, we see that our PLMs do satisfy this equation. So that's the derivation of the fact that the associated Legendre polynomials are this factor, which is sine of theta to the power m. So sine theta to the m times the mth derivative of the lth Legendre polynomial of cosine theta. All right, that's a big mouthful. And they're it's the mouthful in terms of mathematics is much nicer. And then one can use Rodriguez's formula to write the definition of PLM somewhat more simply. That is to say, we know that PL is an elfth derivative of this expression. And so we just differentiate another m times and multiply by this factor. This formula extends the associated Legendre polynomials to negative values of the integer m. At least as long as m is not less than minus L. And tells us that under reflections, the parity of PLM of x is minus 1 to the L plus m. So you might wonder what is going on with my notation here. Well, there are two notations for the associated Legendre polynomial. One is P sub LM, and another one is PL super M. And they're both very common. I don't know which is more standard. I should probably have just used one. But anyway, they are basically the same. So we've got, when you let x go to minus x, x squared doesn't change, but we have L plus m derivatives, and we learned back in chapter 6 that derivatives have parity minus 1. So the parity of the associated Legendre polynomial PLM is minus 1 to the L plus m. And this, of course, occurs all the time in atomic physics and leads to selection rules. Now, this formula here, 1907, of course, makes sense only if L plus m is non-negative. And so m can't be less than minus L, and m can't be greater than m, because if it is, then you have more than 2L derivatives of a polynomial that's just of order 2L, and so you get 0. So this gives the condition that m has to be between L and minus L. This is something that occurs in spherically symmetric quantum mechanics problems or non-relativistic quantum mechanics. Since m only occurs as m squared in the differential equation for the associated Legendre polynomial, PL minus m has to be proportional to PLM, and in fact, this is the numerical relationship. And if m is non-negative, then you see that if m is not equal to 0, then P Lm of x has a power of square root of 1 minus x squared in it. And so PLM of plus or minus 1 is equal to 0. Actually, that kind of is obvious if M is positive. If M is actually negative, then this requires a more subtle analysis. So let me make a note to myself about that. But nonetheless, it's true that PLM vanishes here. Now, our self-adjoint differential equation for the associated Legendre polynomials is this. And looking at it, you can say, well, we could regard LL plus 1 as the eigenvalue. In that case, the weight function is unity, and this ordinary differential equation is self-adjoint on this interval. At the end of it, P of x, which is this thing, 1 minus x squared, vanishes. So the eigenfunctions must be orthogonal on the interval. And the full integral formula turns out to be this. And the weight function you see is unity. And the orthogonality is in the eigenvalues, L and L prime, where M is constant. M is the same. On the other hand, you can take M squared to be the eigenvalue and keep L constant. In that case, you get orthogonality in M. But with a weight function, you see if M squared is the eigenvalue, then the weight function is 1 over, or minus 1 over 1 minus x squared. Actually, just 1 over 1 minus x squared. And so the weighted orthogonality integral is this, and the orthogonality here is delta M, M prime. We can see that if M squared are the eigenvalues, well, we can't have M going to infinity. But if L is the eigenvalue, we can have L going to infinity. And as L goes to infinity, LL plus 1 goes to infinity. And so these Legendre polynomials are, the associated Legendre polynomials are complete, as are the ordinary Legendre polynomials. Spherical harmonics. Well, we're basically done. In a sense, we're done with this chapter. The spherical harmonics are just the product of the associated Legendre polynomials times the azimuth functions e to the im phi, and we divide there by square root of 2 pi to have nice normalization in phi, and then we have normalization for theta by having this huge square root with a minus 1 to the m. The minus 1 to the m cancels the dependence here. Well, let me skip that for the moment. So let's see. The orthogonality is this, and now we have orthogonality in L and M. And the orthogonality in M is obvious. This is just what we learned with Fourier series. And so we have delta M, M prime. The orthogonality in L is what we learned a moment ago, namely that the weight function was unity for the associated Legendre polynomials. And they're orthogonal for different eigenvalues, L. And the numerical relation is this, and the reason for the crazy square root and the minus 1 to the m is so that we have y lm star times y l prime m prime integrated over the unit sphere to be delta L, L prime, delta M, M prime. So we want a 1 here, and for that reason we have these crazy factors. The parity transformation in spherical coordinates is that x prime is minus x. And so r prime is r. Theta prime is pi minus theta, and phi prime is phi plus or minus pi. So under parity, cosine theta prime is, well, it's pi minus theta, and that turns the cosine into, it gives an overall factor of -1. The azimuthal factor, the im phi, gets a -1 to the m, which is e to the I m pi. And this -1 to the m cancels the m dependence of this under parity. And so the total parity of the spherical harmonic is just depends on L. And so it's just -1 to the L. So that's the reason basically for this. I guess there are two reasons for this. One is, well, no, it wouldn't matter because it would be squared here. But the real reason for this is to cancel this -1 to the m, so that under reflection, x goes to -x, spatial reflection. I'm sorry about this. This mouse is just so incredibly sensitive. I must give the mouse some cheese, I guess. Anyway, under parity, the spherical harmonic then changes by -1 to the L. And so parity of this state, which involves a spherical harmonic, is -1 to the L. And that's, as I said, the origin of various selection rules in atomic physics. The spherical harmonics are complete on the unit sphere, and they may be used to expand any smooth function in this way. And the orthogonality relation says that the coefficients are, well, if you just write F as ALM, YLM, and then you use this orthogonality relation, you can see that ALM is equal to this. And this is basically the same thing as an echo of what we did when we did Fourier series. If we put the two equations together, we can write F as, here's ALM. ALM is this integral. It's the integral over phi prime and theta prime of f of theta prime phi prime. That's this with a YLM star, and this YLM is that. So the A is the integral. It's everything except the capital Y in this equation is the A, and then the capital Y comes from here. So we have this equation. But on the other hand, that means that the thing inside the square brackets is a delta function. And so this is a delta function on the unit sphere. And it has an extra 1 over sine theta to cancel this. And some people abbreviate this as YLM of omega, and they call it delta 2 of omega minus omega prime. Anyway, we had a spherical harmonic expansion of the Legendre polynomial of the cosine of n hat dot n hat prime, where these are unit vectors in which the polar angles say, or if the polar angles are theta phi and theta prime phi prime, then this formula, well, the formula that was right up there for the Legendre polynomials is just this. And this is then called the addition theorem. And it's derived in example 1121. That's a derivation in terms of group theory. Okay. let's see, we haven't had many questions tonight. In fact, I think we've had 0 questions tonight. So how about some questions? I'll say a few things about the cosmic microwave background as an application of spherical harmonics, but I think it's more important for me to answer questions. So you should please put them in the, okay, so if somebody wants the CMB. All right, well, do put a question on the chat or just shout it out. I don't think it matters that much, in as much as your faces aren't being recorded. I don't think it matters if you shout it out. All right, the CMB. Well, there's the instruments on the Wilkinson microwave anisotropy probe, which is called WMAP, and also the Planck satellites. The Planck satellites being at the Lagrange point, L2. Sorry about this. This mouse is so damn sensitive. Anyway, this Lagrange point L2, by the way, is in the shadow of the Earth. And it's about 1.5 million kilometers farther from the sun than the Earth. And it just follows the Earth around the sun. And it sits in the shadow of the Earth because you want the instrument to be as cold as possible, because it's measuring the microwave background radiation, which is at basically 3 degrees, 2.7 degrees Kelvin, which is very cold. And they measured the temperature as a function of the polar angles. And the picture of that is this very nice picture. Red is a little bit warm, but notice it's only 300 microkelvin warm, whereas the actual temperature is 3 Kelvin roughly. And so these are fluctuations of the order of 10 to the minus 4, 1 part in 10,000. So in other words, the microwave sky is enormously uniform. And that's why when these, the people who discovered it, who were actually at Bell Labs, which was in or near Princeton, New Jersey, was something operated, it was an industrial lab operated by AT&T. AT&T then had such a monopoly on telephone service that it performed various public services for free, and one of them was Bell Labs, and another was Sandia. They managed Sandia during the Second World War. Anyway, this is the, I think I could look at this for a very long time. This gray thing is the outline of the of our galaxy, the Milky Way, in other words. And of course, this is these are the coordinates of the sky. So this is the whole sky written in as a 2-dimensional plot. And so basically what was happening was that up until about 380,000 years after the time of infinite temperature, or infinite redshift, the photons were interacting with atoms and well, not so much. I mean, as you go back in time, the temperature goes up, and as a result, you have, as you go back in time, you have a lot of hydrogen gas and helium gas, but then as you go before 380,000 years after the Big Bang, the temperature becomes so hot that hydrogen and helium are no longer stable, and So you just have electrons and nuclei shooting around, and then at earlier times, even the nuclei aren't held together, and you just have protons, neutrons, and electrons and neutrinos, and whatever dark matter is. We have no idea what that is, and in fact, the humbling factor is that fact is that there's 5 times as much dark matter as matter. By the way, the dark matter should be called invisible matter. That would be a much better use of language. But when the universe had cooled enough so that and that was basically 380,000 years after the Big Bang, the temperature dropped to about 3,000 Kelvin. Now, of course, that's 1,000 times hotter than the background radiation is now. And that was cool enough for hydrogen atoms to be stable. And this initial transparency is when the photons decoupled from the atoms. And so basically the photons were no longer energetic enough to excite, to ionize hydrogen, or even to knock the ground state hydrogen atom into its first excited state. And the point here is, of course, that the photons are never all at exactly the same energy. If they're at a given temperature, that's a Planck distribution of the energies. And so when you're at 3,000 Kelvin, the point is that the average photon is, well, I forget what the actual the actual energy is, but it's such that I think actually you divide by 40. Anyway, let me not try to do that in my head. The point is that at the time of decoupling, even the photons in the tail, the high energy tail of the Planck distribution, were not energetic enough to knock hydrogen atoms from the ground state into the first excited state. So at that point, the hydrogen gas became transparent. The helium gas was already transparent because the energy levels are higher for helium. And this is sometimes called recombination, but of course, it's recombination only if you have a cosmology in which you have a bouncing universe, which may be true. But anyhow, so the spherical harmonics are complete on the sphere, so we can expand the temperature in terms of the spherical harmonics. The spherical harmonic coefficients then are given by these integrals. The Planck people define a sum over m of the absolute value squares of these coefficients divided by 2L plus 1 as C sub L. And they then multiply C sub L by LL plus 1 divided by 2 pi. And I call that D sub L. And that's what they're plotting here as red dots. And you can see that the errors increase as you go to the left. That's the reason for that is actually statistical in part, because as you go to the right, you've got smaller distances, higher L's, and as you go to the left, you have lower L's and larger distances. Remember, the cosine is the PL for L equals 1. PL is just cosine theta, and so it's sensitive to the whole region of the whole sky. And so the point is that the there's really at any given time, there's only one value of the D1 and of the D1 coefficient, because it's sampled from the whole sky. Whereas at a given time, this thing is like 1 part in 1,000 of the sky. And so the Planck telescopes get 1,000 different samples of the high multiples where at a time in an observing time where they only get 1 sample of the whole sky, the PL equal to 1 or 2. And so just for statistical reasons, these errors start to grow larger here. At any rate, this, if you combine these various definitions together, you see that C sub L is 1 over 4 pi, integrals over, double integral over the whole sphere, a Legendre polynomial, and then the actual temperature, observed temperature at the 2 different points on the unit sphere. And this power spectrum then is a snapshot at the moment of initial transparency of the temperature distribution of the rapidly expanding plasma, of photons, electrons, and nuclei undergoing tiny acoustic oscillations. So in these oscillations, you've got gravity trying to compress the gas and radiation trying to expand it. And so you can see that if a certain region of gas randomly has a slightly higher density, gravity's been able to compress it, and so that leads to a higher temperature. On the other hand, after it bounces off that, it goes out, and then you have a larger radius, and you have then a rarefication. In other words, the gas has expanded, and it's it spends more time at the minima and at the maxima than in between. That's just the nature of a harmonic oscillator. And so the maximal temperature deviation is, the temperature deviation is maximal when it's most compressed and most rarefied. And the regions that that are squeezed to maximum compression at transparency form the first and highest peak. So this is a region this is the largest region that has compressed, been compressed by gravity. And this is also a compression region. That's a compression region. These are rarefication regions, and so forth down the line. The remarkable thing is that this curve here is fitted with only 6 parameters by the Planck group. And now I should tell you that one of the parameters was fitting the height of the curve at the maximum. So it's not that good. But then the other 5 were physical parameters that correspond to the parameters of the universe, of the early universe at 380,000 years after the Big Bang. And the solid curve is then a prediction of a model called lambda CDM. C stands for cold, D for dark, M. And lambda is a cosmological constant. The cosmological constant is the simplest way of describing what's called dark energy, which is what is in effect an energy density of empty space. And the energy density of empty space causes a negative pressure and causes the expansion of the universe to accelerate. Of course, we have no idea what that is either. One simple way of thinking about it is imagine that you're applying the best physics you know to calculate the energy density of empty space. Well, it's some real number, could be negative, could be positive, could be zero. Chances of it being zero are, in my book, zero. And so it's not surprising that it's small and positive. But I mean, if it were large and positive, we wouldn't be here because nothing ever would have, the universe would have become too spread out for life for intelligent life to evolve. And on the other hand, if it were negative, then it'd be the other way about, and we'd have the acceleration of the universe would have been slowed down, and in fact, the Earth wouldn't have lasted long enough for intelligent life to evolve. Anyhow, the picture here is that the visible universe is 13.8 gigayears or billion years old. That is since the Big Bang. And if your cosmology is a bouncing universe, then it's just since the last bounce. The parameters that went into this, so lambda is the density of dark matter, dark energy, sorry. The Hubble constant is taken as 67.7 kilometers per second per megaparsec. A megaparsec, I understand, is of the order of 3 million light years. And this megaparsec is really a stupid unit. The energy density of the universe is enough to make the universe flat. So that's what lambda is taken to be. And the fraction then of the energy density due to ordinary matter, dark matter, and dark energy are 5%, 26%, and 69%. So there's some question as to what exactly is the right value of this, and but it's within 9% of this. And I should say that this is the percentage of ordinary matter, invisible matter, and dark energy. Well, I could go on to talk about this. I actually wrote a paper which was published in the European Journal of Physics. I wrote a paper on this topic, and I'll add it to the class website, and you can read it. UNM actually doesn't have a subscription to that journal, so I can't give you the published version. I can give you the published version, but not the, I don't think I can download it. Well, maybe I can, I don't know. Anyway, I'll put something on the class website. So let's see, we've got just a little bit of time left. I think it would be good for me to, instead of going on about the CMB, I should be talking about, I should be trying to explain things to you, things that I covered too quickly and that you'd like me to go over more carefully. By the way, the latest news from cosmology, of course, is that in the last few years, gravitational waves have been detected. I never thought, I always thought when I heard a colloquium on gravitational waves, I always thought they'd never be detected. but in fact, they have been, and it's quite remarkable, and people will be learning a lot from them. I also, by the way, wrote a paper on general relativity with fermions. I think I'll put that on the class website also. And the funny thing about that paper is that I was really just talking about general relativity with fermions, and I just mentioned that, you know, maybe these bosons that I needed would contribute to dark matter, but that's all I said. And the referees came back and said, you should say more about that. And so I did. And when I looked into it, turned out all the experimental limits on these, looking for effects that would be expected to be produced by these bosons. The experiments all say that the bosons have to have at least a certain mass, and they have to be very weakly interacting. Well, if they're weakly interacting, they can't decay very rapidly. And in fact, the limits force the gauge bosons to be part of dark matter. In fact, the one can pose another limit, saying that for them not to be all of dark matter, they have to lie within a certain region. All right, enough of that. We've got 4 minutes left. I really should say something else about something. Maybe I'll just say something about this last paragraph here. The radius of the maximum causally connected region at transparency is, well, 380,000 light years. That makes sense because it's the time times the speed of light. Actually, that's a little bit, I think maybe one should change that a little bit, because the relationship between distance and time isn't straightforward in an expanding universe. So maybe I ought to think about that just a little more careful, a little more clearly. So top 393. One amusing thing about the expanding universe and the dark energy, which is accelerating the expansion, is that there's a limit to the distance from which we can ever observe light. In other words, if you imagine you've got some immortal beings with really great telescopes, say on the dark side of the moon or something, or at the Lagrange point, and they just wait an infinite amount of time. What is the farthest they can observe? And you'd think if they waited an infinite amount of time, it would be an infinite distance. Well, no, because of the expansion, the accelerated expansion, it's a finite distance. I forget what it is, but it's in that paper that I'll put on the class website. So, well, what we'll do next time, I guess, is go to the next chapter, which is Bessel functions. And now you for the normally when one talks about Bessel functions, one is talking about cylindrical Bessel functions. These are the standard capital J functions as opposed to the little j functions, lowercase j. The lowercase j are the nice spherical Bessel functions. These Bessel functions, you can see, these are very complicated structures here. I mean, they're much more complicated than the spherical Bessel functions. If you look at the first term of the series, you see that for small argument, they're going to be z to the n over a constant 2 to the n over n factorial. And then the alternating signs mean that as you get z bigger, they turn into a cosine. And here they're plotted. These are J0, 1, and 2. Here's J0. But all the others start at 0, and 3, 4, 5 are plotted here. And they look like cosines divided by square root of z for large z. They're entire functions, and we are entirely out of time. So let's try to get more questions because I'm not very good at all at reading minds, especially at a distance through Zoom. And so I just have, I can't know what it is that you want me to talk about other than just to go through the material. Let me say that I'll put this on the on YouTube, and I'm using the new class website for everything except the videos. The videos go on either YouTube or on the UNM website. But the new material, like the examples, for example, this thing here, this is on the new website, which is panda3.phys.unm.edu/ I think ~Kevin/466-20, something like that. Anyway, I'll send you an email with the link, although I've already sent it, but of course, you know, we all get so much email that it's hard to keep track of any email that's already come. All right, well, I'll say goodbye then. Oh, thank you. Isn't that nice? Thanks very much. So I guessed correctly after all. So everyone sent, Havarti has sent out, oh, I shouldn't say anybody's name. Somebody has sent out the website. In fact, why don't I why don't I wake this thing up? Ooh. And just add, I'll just add that then. So you go to panda3.phys.unm.edu /Kevin and then /466-20. And you can add another slash if you want to, but I don't think you really need to. Okay, so I'm gonna say good night. Stay safe, and remember, this is an airborne virus, so stay out of bars, stay out of indoor crowds. That's the worst, indoor crowds, especially if they don't have masks. And thank you, and have a nice evening, everybody. So I'll stop share.
Thank you very much.
Thank you. Have a good one.
Yeah, you too. Thanks. Bye. And